Yeah. Are you able to see this?
Yes, ma'am.
Yes, ma'am.
Okay. So now this is a new paper where I have drawn the final magnitude plot that we had. In the previous sheet, what I had done is I have sketched a reference plot and then I had shifted it upwards by 20 dB to get the final plot. Here, this is the final plot. So here you can see that at omega equal to 1, we have magnitude as 20 dB and the whole graph is shifted upwards. Okay. Now, what we are supposed to do here, we are supposed to find the gain margin and phase margin. Before that, we need to identify omega GC and omega PC. Okay. Now, for omega GC and omega PC, we need to remember the definitions of both. Gain margin and phase margins are calculated from omega GC and omega PC, and omega PC is phase crossover frequency, where the frequency at which the phase plot crosses minus 180 degrees. Okay. Now, in this case, at this point, the phase plot crosses minus 180 degrees. Okay. So we have marked this point and name it as omega PC. Similarly, what is omega GC? Omega GC is gain crossover frequency. So the frequency at which the magnitude plot or gain plot crosses 0 dB. So this is the 0 dB line and this is the point at which it crosses 0 dB. So this is frequency which is called as omega GC or gain crossover frequency. Now let us come to the calculation of gain margin and phase margin from the plot. So what we are supposed to do is gain margin is calculated from omega PC and phase margin is calculated from omega GC. How? Now omega PC point we have, just take it upwards, draw a dotted line till it intersects with your gain plot. Okay, at this point it intersects. So this much is the gain margin, this much is the margin that can be added to the system till the system becomes unstable. So this much is the gain margin which I have calculated from the graph as around 21 dB. This has to be precise, but when you have semi-log paper, it will be better for the calculation. Okay. Similarly, phase margin is calculated from omega GC. Now mark omega GC and draw a dotted line till it crosses phase plot at this point. Okay. And this much amount of phase can be added till the system becomes unstable. Okay. So this value is known as phase margin. In phase, you can calculate it. I have calculated it around 33 degrees. So gain margin is 21 dB. Phase margin is 33 degrees. Both are positive, and so the system is said to be stable. Now you might have question, how can we say that both are positive? Now just take a look at this one. Okay, let me just erase. Okay. Now here this point, what is this point? Say minus 21 dB at this scale. Okay. From minus 21 dB, you are supposed to go to 0 dB. So how much do you need to add? Plus 21 dB, right? So for that, this plus 21 dB is considered to be the gain margin and it is considered positive. The calculation for phase margin is little bit different. All the angles that we are marking are negative angles, right? And this negative sign does not indicate that the angle is negative, but it indicates the direction of the angle. And if all the angles are negative, that means the angles are getting added in the same direction, right? So in this case, you might ignore this negative sign for checking whether the phase margin is positive or negative, and then you can see here, this is around what is it, the value 133 or something, or 134, 135, and then you can calculate it up to 180. You are at 135, for example, and you are going towards 180, ignoring the sign. I hope you have understood why are we ignoring the sign, because all the angles are negative. We are keeping, or we are getting the angles added in the same direction, not in opposite direction. If it would have been in opposite direction, then that would have been considered as negative. But here we are adding it in the same direction, so we are having positive phase margin. So that is why phase margin and gain margin both are positive, and then the system is said to be stable. Okay, so this is how it is done. Let me just revise again what we did. We have this magnitude plot, we have phase plot. From phase plot, you identify omega PC, that is phase crossover frequency, the point at which it crosses, phase plot crosses minus 180 degrees. You identify omega GC in the gain plot when it crosses 0 dB. Then take the lines upwards, draw dotted lines till it intersects gain plot. Same happens with omega GC. Take this line down and draw it till it crosses phase plot, and then this would be the actual, on the scale you need to calculate what is gain margin, and from this phase margin. So please remember that gain margin is calculated from omega PC and phase margin is calculated from omega GC. When both are positive, the system is stable. It might happen in some problems that phase margin is infinity, or phase margin is 90 degrees, gain margin is infinity. It might be anything. As long as it is positive, the system is said to be stable. Okay. Now please let me know whether you have understood it or not.
Yes, ma'am.
All of you?
Yes, ma'am.
Okay.
Yes, ma'am.
Yes, ma'am.
Okay. So now what I'll do is I'll just share a screen with you, which I have obtained using MATLAB. In MATLAB, you just need to give two commands by providing the actual transfer function. It will return the Bode plot to you. Only thing is that this Bode plot, the magnitude plot and phase plot, please understand this magnitude plot is not asymptotic in case of MATLAB. When we have semilog paper, we must draw asymptotic plot. This in the MATLAB, we do not get asymptotic plot, but still we get the shape of the magnitude plot. Okay. Now there are few things to notice, so I'll just mention them. Magnitude in dB. Okay. So this is 0 dB line. Here we have minus 180 degrees. In this particular case, in this particular problem, what I had shown to you was the random phase plot. I had not plotted it as per the calculations in the phase plot. In this particular problem, as you can see, the phase plot is not crossing minus 180 degrees. It is just going along minus 180 degrees. It is not crossing. That means you're not going to get omega PC. Okay. Or omega PC can be considered to be at infinity. In that case, you will get, now at infinity, suppose you get omega PC. In that case, you will get phase margin equal to infinity plus infinity, because gain plot has already crossed this line. Now this point is nothing but omega GC. You can take this down, and then this much would be the phase margin. Okay. So in this particular problem, we can see this. Now, most importantly, you can see on this scale, we have a semilog paper in the background, semilog grid, you can see. So this is how the semilog paper looks. You can see the frequencies 10 raised to minus 1, that is 0.1, then 10 raised to 0 is 1, then 10, 100, 1000, and so on. And these are the spannings of a decade. So each one of these are known as decade. And what I was telling is, you mark the point, say 20, 40, and say 60. For example, I'm showing this will be slope per decade. That will be the reference line that you will draw. Okay. And then you will draw the lines parallel to these lines for sketching the appropriate plots, appropriate slopes. Okay. So this is how the Bode plot works. Now, one last point I would like to mention here. Now what we have is, in your actually, I mean, this part was this topic is part of 4th unit, and you were supposed to solve online